Crash Course Instrumentation, Episode 35, Terminal Blocks, Tolerances, and Real-World Wiring. In today's episode, we bridge the gap between clean theoretical circuits and the messy reality of wiring panels, component tolerances, and terminal blocks. Welcome to the real world of resistance, terminal blocks and resistors in the field. When you measure resistance in a classroom demo, everything looks neat. But in the field, that resistor is wired to a terminal strip, screwed into a DIN rail with maybe 3 extra feet of copper between it and your meter. That extra length and those mechanical connections add resistance. It may only be milliohms, but in low resistance or high precision circuits, it matters. Case study, terminal block loop resistance. Let's say you're measuring a 100 ohm RTD sensor loop and get 104 ohms. That 4 ohms could be from lead wire resistance, terminal oxidation, loose screws, or poor ferrule crimping technique. What does an RTD stands for? Resistance Temperature Detector. It's a temperature sensor that works by changing resistance as temperature changes. Most RTDs are made from platinum due to its stable and repeatable resistance characteristics. The most common standard is the PT100, which has exactly 100 ohms of resistance at 0 degree. As temperature rises, so does the resistance, typically about 0.385 ohms per degree Celsius for a standard PT100 RTD. These sensors are used across process industries due to their precision and stability. But that precision means every connection point and every foot of wire matters. Always clean and tighten terminals before assuming the sensor is off. Remember KISS. Keep it simple, stupid. It is usually the most obvious and simplest explanation. Tolerances matter. Resistors are not exact. That 1,000 ohm resistor could actually be 990 ohms, 1% low, 1010 ohms, 1% high. How to read tolerance. Gold band equal plus to 5%. Silver band E plus to 10%. Brown E plus to 1%. Red E plus to 2%. A 1,000 ohm plus or 5% resistor may be anywhere between 950 and 1050 ohms and still be in spec. What you see on your meter is the sum total of everything in the path. Component resistance, lead wire length, terminal resistance, contact cleanliness. So if your reading seems a bit off, it might not be the component, it might be the connections. Fun fact, military and aerospace specs often call for 0.1% or tighter resistor tolerances. These are laser-trimmed, cost more, and are used where precision absolutely matters. Technician takeaway. Always read resistor tolerances before assuming a failure. Use 4-wire Kelvin measurements for low-resistance precision work. Don't overlook terminal blocks, clean, crimp, and torque correctly, and understand the role of RTDs and their sensitivity to wiring and connection conditions. Always perform a tug test after terminating your wiring. Next time, we'll explore how analog energy models, like our plumbing analogy, tie into power dissipation using Joule's law. Like, share, and subscribe so you don't miss what's next on Crash Course Instrumentation.